Welcome to Beyond the Microchip, brought to you by Microchip Technology. In part one of our two-part episode on space-inspired tech in our everyday lives, we discussed how necessity created many of the modern technologies we rely on, and we're reminded that the distance between the cosmic and the commonplace isn't as far as we might think. In part two, we continue our conversation of these ideas and dive into the products and systems that support humanity's desire to explore the extraterrestrial world high above us. Thanks for listening. Let's go beyond the microchip and hear a story of empowering innovation to enhance the human experience. So let's get back to the radiation component of it. There is a definite concern about radiation, and then there are techniques that we use to mitigate that radiation. So you mentioned rad tolerant. What else is there? What else is there for radiation mitigation?
So, like we said earlier, when you're flying in space, you're exposing electronics to the effects of radiation,
Right.
which can severely degrade the performance of the circuits and in this case, degrade the performance of the system, which is our cordless drill. So through decades of design and development, we understand what it takes to mitigate these factors within our solutions. And that enables us to provide rad tolerant or rad hard by design, as it's sometimes called, solutions that we can deliver with full confidence of their immunity to these effects. And with that, you know, when you use a microchip rad tolerant or rad hard device in a space application, you can be assured that you will have mission success.
What do we know about that process? Is it all confidential, or is there anything that we can share with the public?
No, I think it's a matter of some public information. When we talked about latch up, that's an intrinsic side effect, if you will, of what's known as CMOS, which is what most integrated circuits are today. If you want to look that up, it's CMOS, complementary metal oxide semiconductor. It's the way in which the semiconductor is fabricated. But unfortunately, there's an aspect that comes with CMOS that makes it prone to latch up. And these are called parasitic transistors that just have to exist in the architecture. Knowing that full well, if we take those into consideration at the very early stages of development on a device, we can understand what it takes to deliver a device that's immune, even though it carries these parasitic devices within it.
So is that where the radiation, what would we call it? Is it encasing? Is it a coating? Is it just how
Nope.
is it a packaging?
Nope. In the case of total ionizing dose that we talked about earlier,
Yeah.
yes, that is helped by shielding. Can actually resolve a lot of those issues with shielding. We've been doing that for decades. But single event latch up and the single event upset we talked about, there is no effective shielding to protect you in space from those effects. So your device is either immune to it or susceptible to it.
So it helps that somebody that understands this technology is how you want to design in, right?
Yeah, it's interesting what Eli was talking about the parasitic transistors. Those are just laws of physics. That's standard solid-state physics. Everybody understands what causes them. Everyone understands how to lessen the effect or the proclivity of actually a latch-up event occurring. But there's a lot of other mitigations and accommodations that are in play in the industry regarding radiation include a lot of different techniques. Some are internal. We talked about the error correction and detection in memory earlier. An accommodation example would be measuring the current in a latch-up consideration and being able to intercept that very quickly. If you don't intercept it quickly enough, obviously it's too late. But there's accommodation methods as well, and there's system-level considerations like redundancy of systems. And there's other techniques as well around mitigation and the accommodation that are in play all the time. And the industry is always looking for how to elevate that because it permits much more latitude about how you engage with the actual semiconductor, rad hard, rad tolerant, which goes back really to the mission that Eli talked about earlier. How long is the mission going to last? The duration, which goes back to the TID aspect of it. So it's a very, very deep science. I would say 40, 50 years ago, it was rad hard, rad tolerant, and that was your choices. Now the technology around it at a system level is elevated significantly. It's a fascinating place to play and to be engaged with day to day.
So how would you define accommodation versus mitigation? Because I threw around the mitigation word as kind of a catch-all, but that's not how NASA sees it.
Right. So let me give you a practical example. So every time I open my front door, it's got this nasty squeak. And I just live with it. I'm accommodated. I open it slowly. It doesn't squeak if I open it slowly. It only squeaks when I open it quickly. So I accommodate it. I live with it. Mitigated is I get out some lubrication again and I lubricate the hinges. Now it's gone. The same thing with electronics. You can live with it and try to accommodate it, or you can mitigate it. Bill referenced measuring the current. Clearly, you can detect that a latch up is coming because, as we said, that's the demand for an immense amount of current by your system, well above anything you could imagine. Well, if I'm measuring that current, I could say, oops, got to turn this off. Well, but guess what? The measurement of that current, the ability to turn it off, the ability to detect it and control it, all those functions have to be rad hard. They can't be susceptible in and of themselves. So you've just added more components to your system. And we all know more is not always good. More components usually mean lower reliability.
And complexity.
And complexity, which is never really a good solution. So in our opinion, our best solution is to have it mitigated in the first place. Don't accommodate it. And use devices, use solutions that have full mitigation against these radiation effects.
So there's all the planning that goes into this. You have to be able to know exactly what's going to happen. And that's why launches get delayed, because you got to hit this tight window. So is there a fluctuation in the amount of accommodation that goes into a mission critical plan? Or is it limited as much as possible and accommodation is an accident?
Well, that depends on your tolerance for risk. It depends on your mission. Things have changed in the last, I'll say, 10 years, where tolerance for risk has gone way up. Back in the day, the words good enough for me in the space business could never be applied. I probably would have been fired if I used the words good enough. But then again, back in the day, we designed satellites for 15-year missions that wound up lasting 30 years. Is that a good thing? Well, it depends on what side of the fence you're on. 15 years into a mission, has the technology evolved? And should that satellite be replaced? Or is there some utility? You can argue both sides. Let's take a look at Voyager.
Yeah.
My favorite.
How long has Voyager been out there? Bill?
Voyager launched, I believe, in 73.
73.
Over 50 years.
Mm-hmm. And here it is, 24.
What was the duty cycle on Voyager? Did they expect it to last a certain amount of time?
5-year mission.
But
like Star Trek 5-year mission?
5-year mission, yep. Mm-hmm.
But
wasn't going to make it to the end of the solar system in 5 years.
But back in the day, the design constraints were extremely tight.
Yeah.
Because we didn't know what to expect. So the margins, for the design margins, for example, were enormous. The constraints we operated in, huge. The cold standby, which I believe we have now employed on Voyager. I think they've called on a cold standby system to save the mission.
Mm-hmm.
So you could imagine 50 years ago, the technology was wildly different than it is today. But the design standards for sending something up into the unknown were extremely conservative, and that's what drove a lot of the cost early on.
So will the increase in accommodation, will that inspire more people to want to send stuff up?
You mean the increase in mitigation? Is that what you mean?
No, he means accommodation.
Well, so let's get back to what you were talking about earlier. Well, the squeak in the door, now that more squeaks in the door are practical reality, do you think that will encourage more people to want to put things up there?
I think it has. I think the proof's sort of in the pudding between.
I agree a lot. I think that more people are seeing that the barriers to being in space might be lower. But I think also what you have right now are a lot of new companies that have not yet put anything into space, particularly into deep space. And they're going to find out, I think, when they get there, they may have accommodated a little bit too much. So the pendulum's going to swing back in a different direction in the coming years.
And we really need to discuss that. There's space, and then there's deep space.
Yeah, are we getting into Leo, Meo, and Geo at this point?
Okay. Correct.
Yeah.
I mean, if you're in Leo, most
that would
likely
be low Earth orbit.
Yep. Most likely your mission duration is not very long. Just by virtue of the size of your spacecraft, your mission, how much fuel you can carry. Because don't forget, once you go into space, you have to maintain your position, so to speak, on station.
Yeah, talk about that. So once you get up there, it doesn't just stay there.
That's correct. You have to maintain your orientation so that, for example, your solar arrays are facing the sun, your antennas are facing Earth, and you also are constantly being drawn back to the Earth by gravity. Even though you're out there, you're not beyond Earth's gravity, right? And so to maintain that, you're either flying at a certain speed to keep that elevation, or if you can't afford that, and let's say you're in a geosynchronous orbit or some type of orbit where you can't afford that speed, then you have to maintain your position through the use of fuel or whatever it takes to maintain that.
Yeah, so satellites run out of gas?
Absolutely.
Mm-hmm. Yeah, the ones that use propellant do, yeah, absolutely. There's ways to do some of this actuation, the motion control, without propellant, but it's as a special case, I would say, be the best way to put it. I think the accommodation side of it is interesting because we talked earlier, we started with the idea of what up there has come down here.
Right.
And I think we can talk about what we're talking about right now is really something up there that is up there again. If you look at companies like SpaceX, Rocket Lab that are doing this low Earth orbit approach, and this is very low Earth orbit. I'll call it LEO light, actually, and we'll get a little bit into that in a moment. For those companies, they are using a lot of technology and innovation from NASA's portfolio and their rocket systems and whatnot. So a lot of this NASA pedigree is still being used in space, but in this commercialization of space by private companies. So that's there as well. And we should never forget that what these companies have done is really unbelievable from a technology perspective, the sheer number of launches and this sort of thing. But it still has a NASA lineage for sure.
What are some of the considerations of going into deeper orbit?
I'd like to start by adding on to this idea. I'd mentioned LEO Light is this really, really low Earth orbit commercialization arena, altitude. Then you actually have what's still within the confines of LEO, more of the government and defense-based satellites, and those really have to have rad-hard, rad-tolerant components.
But there's a reason why, even though they're in LEO. And that's because we talked about the magnetic field, right, protecting us and our spacecraft in LEO from the excesses of radiation. However, what happens to our magnetic field at the North and South Pole? Well, it collapses. So if you're flying a so-called polar orbit, even though you're in LEO, you get to go through, effectively, no magnetic field.
That's that diagram of the Earth with the lines going around.
That's correct.
Yeah.
And when you fly through that, you experience the same radiation levels you would have in a geosynchronous orbit, which is some 22,000 miles out into space, only by virtue of the fact that you forfeited the magnetic field by requiring, let's say, a polar orbit, which many of our defense applications require.
So there's a separate design consideration for the equator versus the poles then?
Absolutely.
Very much so.
In LEO, absolutely.
But not as you get up to GEO because you're farther away from the Earth's magnetic pole.
Then you have the...
Yeah, then you're fully exposed.
Right.
to what space provides you, which is nothing particularly good when it comes to radiation.
No, not based on what Eli's been telling us.
That's right. So there's the GEO, which is the geosynchronous Earth orbit, which is very cool in that the satellite can stay over the same point on the Earth. There's also MEO. I think that's going to be medium Earth orbit.
Yep.
And then there is HEO, highly elliptical orbit.
Yep.
Which goes back to a lot of government and defense applications. And now we're getting into a new arena between that MEO, GEO, and the moon, cislunar, and then, of course, there's always been lunar and then interplanetary. So it's really getting chopped up pretty fine now. And it's largely defined around application, which now for the commercial side of things goes back to business model.
Right.
How much money am I willing to put into this? Where's my trade-off on risk? Where's my trust in my team? And it's a very, very interesting dynamic right now in the commercialization of space. And now we're starting to get off into business topics rather than semiconductor, but they're all still somewhat related.
Getting back to the magnetic field, though.
Yes.
Some of our listeners may not appreciate an anomaly that exists on the planet called the SAA, the South Atlantic Anomaly. And when I learned about this many years ago, my jaw dropped. Turns out there's a region on Earth in the South Atlantic where the magnetic field has a hole. And if you have a spacecraft and it flies through the SAA, which you can look up, South Atlantic Anomaly, I'm not making this up, I promise, you'll be shocked. And it's just an incredible phenomenon.
There a reason there's no Argentinian space agency then?
I don't know how close it is to Argentina, but...
well, it turns out Argentina has an excellent space agency, but I was going to ask Eli, this SAA, any idea on what causes it?
So I think there's a lot of theories. I've read about it over the years. I just think it's, there's this rotating ball of molten nickel, right? Allegedly, at the core of the Earth. And that spinning ball is what produces the protective magnetic field on the planet. And for whatever reason, a defect exists in the flow or rotation of that ball where the magnetic field just takes a dip. And it's incredible.
And that's the South Atlantic Anomaly.
Yes, sir.
Okay, well, I have two things that I want to get to. One is this concept of heritage, which we've had plenty of discussions on, but I think we should probably talk about it here. And the other is scalability. And where should we start? Want to start with heritage?
Yes, let's start there.
All right, so mission-critical applications requiring accommodation and mitigation. But clearly, even with the recent developments of the SpaceX capturing the booster and the chopsticks, which was remarkable, it's still, nobody's going into space tomorrow. This takes time, right? Is that where heritage comes in?
I think without a doubt, one of the key elements to utilizing one of our solutions is whether or not it has a history in space. And that's important because that's sort of proof in the pudding. It's been up there, it's flown, it's been successful. I'll give you a case in point that's very close to my experience. We manufacture a DC-DC converter, which is very unique in its design. It's a module, and it typically takes as an input spacecraft voltage, which could be anywhere from 28 to 120 volts DC. This is generated by the solar rays, stored by the batteries, processed by electronics to create a bus voltage, almost like an outlet voltage in your house, except that it's DC. And this converter effectively steps down that voltage, much like the plug you have for your charger for your phone, steps it down to something the phone can use. This DC-DC converter steps down the so-called bus voltage on the spacecraft for an application. Could be a processor, could be a sensor, some application on the spacecraft. Well, this particular design of this solution that we make, this DC-DC converter, the SA50 model number, has a 30-year history with absolutely having had never a single failure in space. That's the ultimate definition of heritage. And there's a real reason why this particular product has that performance. A lot of it not only is involved with the devices that are used, but also the way the devices are packaged. It turns out this design uses small circuit boards, and each of the devices in the design are individually packaged. Now, it may not sound odd that that's the case, but many products are designed with bare die, so-called bare chips. And those chips are mounted and then integrated into a solution. Well, those so-called hybrid packaging solutions oftentimes don't yield the same type of longevity. Thermal cycles, stress, strain, things of that nature. That something would, as a prepackaged, pre-screened, finished solution would as part of the implementation. And that's exactly what the SA50 is. I think there's some pictures on our website that have a cover removed, and you can peer inside, and lo and behold, there it is, a little circuit board with all the devices mounted on it. And so that's a pretty heavy definition of heritage.
I think another piece of the heritage is that you can simulate, you can test all you want on the ground. Simulation by computer, testing in a test facility, actually exposing your product to a radiation beam, but nothing really mimics space, particularly in these deeper missions, these higher altitudes. So the flight heritage, the number of missions you've been on, the kinds of missions, the years you've been active on those missions is your best pedigree by far.
And it's not just radiation, because we're talking about, let's go back to the SA50 or any one of our devices. It was installed, mounted, launched, potentially ejected from the launch vehicle. All of that vibration and shock and performance before it actually even got on orbit was even turned on or even started to experience any of the radiation effects, all create a full scenario for the heritage definition.
Yeah, I'm reminded of a quote from somebody working at Bosch Automotive is, you take it, you shake it, you bake it, and you break it.
Yep.
And if it passes all those, you're good to go.
Yep.
All right, so we've covered heritage. Let's get on to scalability. What are when we talk about that word, what are we talking about in terms of aerospace?
So in terms of our solutions, we offer a tremendous capability to use our products in what we call a pin-for-pin compatible application. So, for example, I can go and purchase a very low-cost microcontroller that's used in everyday applications like washing machines and coffee makers. And Microchip delivers a full space-grade equivalent of that part in form, fit, and function, which means I can go off with a very inexpensive solution, develop the hardware, develop the software, develop the complete function using that microcontroller, do all the testing, all the evaluation, all the analysis, and then extract that component from the design and replace it with a fully space-qualified device that is radiation immune without changing any of the hardware or any of the software that I developed to that point in time. That scalability offers our clients a solution that is extremely low cost and very quick in terms of product to market. Because if I had a software team, I can give them a complete set of evaluation boards, for example, or solutions at very low cost. And the same goes for the hardware team. And they can be running in parallel, knowing that in the end, I'll replace those components with our scalable, ride hard by design solutions as a drop-in. That's what we mean by form, fit, and function, pin-for-pin compatible replacement. I don't change any of the artwork on the circuit board. I don't change any of the implementation that I've made to that point with the, if you will, washing machine part.
So it gives full confidence of the choices available.
Yep.
Yeah, it gives the full confidence. And this is a business model that's being driven into the space players. And I'm talking about the primes. Our government and others are saying that we're going to reduce your budget for development. We're going to reduce your time to develop. There's no longer the time to make the perfect satellite solution program by program. They have to build up IP, for lack of a better term, around hardware and software that they can reuse over and over and over again as a foundation. And that's exactly what scalability supports.
So we were thinking about the commercial aspects of it. If somebody were willing to go into either, we have Leo, Mio, Geo, and then all the different flavors in between, this would allow them to determine how far away and for how long? Is that an oversimplification?
That's true. We do make devices that are at an immunity level that would be suitable for Leo. And we make ride hard by design products that are suitable for Geo. And they're positioned in our portfolio exactly for that type of setting. We call it new space, which is predominantly low Earth orbit. And then there is conventional ride hard by design products for deep space or Geo.
Right, and we're talking about the difference between commercial and exploration.
Yeah, I would say commercial is really the notion of private companies being in space. Obviously, you have some constellations. SpaceX comes to mind. You have multiple launching companies. And there's a whole catalog of small companies that are standing up to support those bigger concepts. As far as 3D printing in space, medical devices, research in space. So the commercialization of it is just beginning. And that's a very, very different business model mindset, investment process as well. Those are all driven by private investment rather than government funds for the most part. So it's just a completely different way to get there that's foundationally unique and different from what we've always done before, which has been agency-driven solutions, agency-driven needs.
All right, so more involvement from the private sector.
Yes, sir. Yeah. Exactly.
So we began our talk today on necessity up there brings benefit down here. This is our crystal ball moment. Now, I'm not going to hold you to it. We're not going to review this episode in 5 years, and I'm going to put your feet to the fire. But in terms of what you think as far as predictions, what kind of things could we possibly look forward to that space necessity would bring benefit down here?
Well, one thing that comes to mind and has been top of mind with me for the last year or so has been the discussion, public discussion in conferences and meetings about building an electrical grid on the moon. Purpose being to grow food, create a habitat for inhabitants, make water, from the water make fuel, and manufacturing on the moon so that that becomes a base from which we go to Mars.
We become the so-called interplanetary species?
Yep. And I think that this will be a reality. But how do you do that? If you look around you, if anyone has cables suspended on telephone poles delivering power to their homes, you'll see those cables are very big, very thick. If you walk up to them, if you're able to walk up to them and not get electrocuted, and put your hand around them, they're about the size of your wrist, even though they don't look it from the ground.
And they're heavy.
Heavy. Even though they're aluminum, most often, they're still very heavy. Well, what are we going to do? Deliver hundreds of tons of cable to the moon to create a grid? Unlikely. So what we have to have on the moon are cables that are extremely thin. You could imagine kite string being the cable. Well, the only way to deliver power, significant amounts of power, over a wire or cable that thin is to increase the voltage, because as your voltage goes up, your current goes down. And when your current is low, you can afford to have very skinny wires. Anyone who has extension cords home knows that the very heavy-duty extension cords are very thick, and the little extension cord you have for a lamp is very flimsy compared to that. And that's because the ability of the wire to carry the current depends on the diameter of the wire. Well, if I don't need to carry a lot of current just because I have very, very high voltage, then I can afford to ship, if you will, spools of kite string, I'm drawing an analogy, to the moon. How do you do that? And why don't we have that on Earth? Where's the capability to deliver that kind of technology? Well, that relies on the development of very high voltage devices that can operate in the irradiation environment that we have on the moon. And we have a number of programs in place to be able to create those kinds of components that can deliver that kind of performance. So as time goes on here, as we prove these out, that's going to be revolutionary. Because when those parts become available, guess what? We're going to implement them back here on Earth. And all of this very heavy-duty, potentially equipment that we have here will be upgraded and remodernized again.
Bill?
I'd like to go back to where we started the whole conversation with the idea of motor control, cordless drills, that sort of thing in space. The idea of motion control in space still advances all the time, and I'd like to talk about two specific companies that I'm aware of. One is Motive Space System, the other is Honeybee Robotics. These are companies that are both tightly related with NASA. For example, Motive provided the robotic arm for the NASA Mars rover.
Okay.
And Honeybee is actually developing a drill system for interplanetary exploration, able to drill kilometers down into icy moons.
Probably not going to be a hand tool.
Not going to be a hand tool, no, sir. So it's this balance between these utilitarian functions of robotic arms, drilling deeply, and science behind it that makes these space-related technologies so much fun to be engaged with.
Great.
Okay. All right. I promised the Motive guys a little.
Well, this has been a great conversation, guys. Thank you so much for coming.
Thank you, Dana.
Eli Quam and Bill Dillard specialize in aerospace and defense applications at Microchip Technology. They join us today from our headquarters in Chandler, Arizona. Thank you for venturing beyond the microchip with us. Join us next time as we continue to explore empowering innovation to enhance the human experience.